Okay, so for this example, what I'm demonstrating here is, let's suppose we had a program that was already written for us, okay? So you inherited this code, and now you were tasked to streamline it, to make it more procedural. And the reason for it is, if you look in here in this program, all of the functionality for this program is done right in main, right? So you don't see any other functions. There are no function calls other than external function calls like square root and or pow, which were defined in the CMath library. But you can see here there are two separate jobs. So let's talk about them first. Well, let's figure out first what is the purpose of this particular program, okay? What does the client want to do? Two things. They want to use Stirling's approximation to calculate factorial, right? To figure out the factorial of a number, okay? And they're providing here the formula for Stirling. And then also they want to compare that to the result obtained by simply doing a factorial with a loop. So basically you have an integer, let's say factorial of 4, so you're going to take 4 times 3 times 2 times 1, your typical way of putting in doing a series of multiplications by subtracting 1 until you reach 1 and you stop. This one does it backwards, so it starts at 1, okay, and it will end when you reach the target. So if you're doing factorial 5, this loop starts at 1, 2, 3, 4, 5. And while it's going through that, it's multiplying each member and doing some form of an accumulation multiplication here. So basically what you have here is fact equal fact times I. So the previous value of fact, multiply I again, and then increment I until this condition is met and then out. Okay? So that's going to give you a typical factorial will do for smaller numbers. Now, what's nice about Stirling, it's an approximation. So let's be precise on that. And notice that unlike a regular factorial, which can be done with integers, this one you don't have a choice. You have a pi that is not an integer. That in it itself is a double. You have e itself also. That is not an integer, okay? Now, by the way, you can go online and Google Stirling's approximation and get more details and try to understand what it's doing, okay? So basically, n factorial, you could use Stirling's approximation to figure out, okay, how close can I get? Then this program does that. It first, you provide it with, let's say you want to figure out what is 9 factorial. So you're provided with 9, and then you're going to do in this code here, which is the loop based on requirement number 2 right here, right? To figure out what the factorial classically might look like. And then notice the second half of the program right here uses Stirling's approximation. So it sets up the ground for that, right? Notice because we want the result to look almost like it's an integer. So this is why they have a fixed and set precision to 0, right? To do this, remember to include the iomanip library file to be able to do that, okay? And then they have a little cute thing going on here where they can actually subtract them from each other and divide by a reference, which will be fact1, right? And multiply by 100 to figure out the percentage difference between these two approaches to figuring out what is the factorial of a certain number. So for this particular compile time program, they want to know what is the factorial of 9 using a for loop with a traditional algorithm for figuring out factorial, and taking that n again, which is part of the equation right here, and right here, and right here, right? And again, I urge you to look up Stirling's formula, right? So simply on Google, and this is the implementation right here of Stirling's formula. And so what they're doing is they're setting the precision to 0, trying to round it up, and then display fact 2, which is the result based on, so you have fact 1 and fact 2, then you're going to compare them. And you're going to see what is the difference between them in terms of percentages, right? What would be an acceptable difference between them, right? In engineering, we call that tolerances. So depending on what you're handling or dealing with, tolerances of 1, 2, 3% can be acceptable. Beyond that, you have some issues. You have to do some compensating things. Again, so not to go in a tangent, this just shows the difference between them in percentage, okay? So not an absolute difference, because that wouldn't make a lot of sense, especially when the numbers are huge, and the difference might be huge and might throw you off. So you want something relative, okay? So this huge number here, relatively speaking, compared to the first one, isn't that far away. And if it isn't, and it's within a certain acceptable tolerance, then you're doing good, okay? Now, there are limitations when you're doing factorials. Factorials really can get huge in terms of result. This is why, notice here, we have an unsigned long. So you're setting up a lot of space for this integer in memory. And the same thing for the Stirling formula's result. It's a long double. Now I'm going to remove that long and show you what issues you can run into in case the numbers are too big and you're surpassing the allocated space for a double. Okay, what will your program do? And if you don't catch that, which we will learn in the future how to handle errors, you can run into a lot of problems. So let's go ahead and run this program. So let me compile and run. Okay, and there you have it. So notice factorial 9, using the traditional method with a for loop, gives me this value. There is a difference, but the difference is only 2%. Okay, let's go for lower numbers. So I'm going to go over here and put a 4, right? So compile and run. Okay, and notice the results are 24. I have a -1%, and that's because your 24 here is not really 24 because I set the precision to 0. It should be at some other number. So let's look at it if we didn't set the precision. So what I can do here is, let me just cut this for a minute, and we'll put it back. So I'm just cut it so it's not gone, right? And let's see what it will do. Same problem. So compile and run. And you can see here that we're getting 23.78888. It's almost -1%, right? That's what you're seeing there. So to round it up, right? So this is, depending again what you're doing, you might say that 23.78888 might be close enough to 24. It's an acceptable tolerance, and you go with that. And again, remember, Stirling is simply doing an approximation. Okay, let's get the numbers even higher. So let's go over here and put a 10. Okay, let's compile and run. Right, and again, I have not removed the fixed and set precision. And you can see here, it already throws a wrench because you're seeing things in powers of 10. And it's saying that the percentage is about 2.2%. Now, if you want to see it kind of similar to what the integer value above for the first method looks like, yeah, sure. Go ahead and do the set precision right here. So let me just Command V, which means basically I'm pasting it back. Let's compile and run with the same number, 10, and see what it does, right? So pretty close to at 2%. When these numbers are huge, right, and you're at 2%, you're not going to be able to see it if it was simply, if I just did a subtraction. It might look too big, and it might throw off your perception. So percentages usually is a good idea to show the difference between two things. Now let's go for bigger numbers. Let's go for 15, right? So compile and run. And now things get a little trickier. Notice the difference gets a little bigger right here. Okay? Right? So, and again, remember, it's an approximation. Stirling's formula is simply an approximation. So let's go for, now this has limitations, so I'm going to be careful. Let me just put 40 here and show you. Compile and run. And there you have it. Now notice my program crashes. Stirling cannot handle, so long double can't handle that large number. And I'm not even sure the first number above is correct. Okay? We probably run out of space right there and then. So one way to figure out if that is true, let's close the program here for a second and do this. Watch this. So I'm going to isolate the first form of operation to see if the error is actually thrown in the second half of the program. This is why it's a good idea to write procedural program. As you can see here, these two ideas are too tightly coupled and they're within the same function and they can create problems. We don't know really where the error really happened at runtime, right? So let's look at it here again. Compile and run now. And now we can see now that clearly it happened on the second half, okay? So I'm gonna just close the program, right? So, but what we would like to do now, let me just put a regular number here for now. Let me save this, is separate these two ideas. One will be factorial. I'm going to call it method 1, and the other one I'm going to call it method 2. Okay? And basically, method 1 will be the Stirling. Method 2 will be this. So, and maybe display the result within method 1 and method 2. So we don't need to return anything to main, unless we want to make the difference or we want to calculate the difference. Why not? Why not? So yeah, so we could have something like this. So that means we could round it up. I don't want to do a typecast of a double into an integer. Let's just display it and then do a void here, method 1, which is going to be Stirling. And this will take an int num, or n if you want. Okay? And I am going to call this one implementation, or the function definition of Stirling. Okay? So this would be the method 1 right here. Okay? So, great. So let's go ahead. So I don't need to see the difference. We know there will be a difference between them. Here's what I'm going to do. I'm going to cut all this right here. Cut it and paste it here. That's method 1. Now, notice I'm not calling it main yet. So it's just hanging by itself right now. There is nothing going on. If I run this program, it will simply run the regular factorial and will not run this part. So just to prove the point, let's compile and run. Oh, by the way, before I do anything, before I save that, I'm going to save this as example 40. So file, save as, and this would be example 40. So there are two different things. There you have it. And save. Fantastic. So our previous version will remain the same, what we had, everything within main, but this version will have things in various functions. Now, let's say if I compile this, just quickly to make sure that I don't have any issues, it compiles fine. Why? Because all of these variables now are local to method 1. And including n right here is also a local variable to method 1. Now, if I run this program, it will simply do factorial of 9 based on the fact, let me just make this a little bigger, that it simply ran what was in main. So it executed what was in main, which is the for loop that you have there. So we want that to be in method 2 instead of main. Okay, notice it never ran method 1. Okay, so let's go ahead and do this. Void method 2. And again, it will take its own variable. And we're going to call this one implementation or okay. So what are we going to do? We're going to copy all of this, cut all of this right here, cut it, and put it here. So as you can see, as a programmer, a lot of times you're going to find yourself modifying things to fit your new strategy. And now in main, we're going to do something interesting. So we're going to do, remember I have this one here, so I'm just going to cut this one. This is part of the deal right here. Otherwise, you're going to have a variable undeclared right here. So Command V, here you go. All right, so, and notice you have to set it to 1 because that's your beginning for the loop. Now, in main, I'm going to ask the user, so this gives me flexibility now. In here, let me just make this a little shorter. Here you go. So I have my 2 methods, right? So let me just compile for now. Compile, notice I shouldn't get any errors. Everything looks good. But if you run it, you're just simply going to press any key to continue because you never called these functions. So if you run this, as you can see, we didn't call these functions. We didn't do anything. But before we call them, notice that they all take a parameter, which means they all will require some sort of an argument value. Aha. So what you need to do now is supply it with that number. Now you could do something like this, method 2, you can call them any order you want, and supply 9, and then method 1 and supply 9. You could do it this way. These will be the function calls. Now we're going to do it a little better than this, but you could quickly test by calling these functions in the order that you choose. And I chose to call method 2 before method 1. Let's see what happens when you do something like that. So compile and run. And there you have it, okay? With a 2% error, right? So now we'll make this program a little more interesting. So instead of just simply calling them and giving them a compile time value, we're going to do this, int num, a local variable num, and I'm going to ask the user, so cout, enter an integer to find its factorial. Okay, and then we're going to do cn num. Now here's what we're going to do. It's up to you which order you want to do this. Method 1, so maybe cout. And you could do something like this, slash n, or yeah, sure, why not? And l, and then call method 1. And supply it with num now. And then this way you could literally see which method you called, right? So cout method 2, or you could call it Sterling, right? And L. And the other one, you could specify what you did in terms of your strategy using a for loop. Okay. And let's put a semicolon here and put method 2 and then supply num. Notice how much more elegant your coding becomes once you separate the jobs. This here does its job, and that's all it does is Sterling. This one does it in a for loop. So yes, the results are kind of the idea is the same. You're looking for factorial either way, but they're two separate approaches. So give them two separate functions, okay? And then give the user a choice maybe. What do you want to use, Stirling or this? So this gives you flexibility in main or in the controlling function to decide if you want to run both of them, one or the other. You could supply it with a number while the program is running instead of at compile time, right? So this will be a runtime program. So let's see how it behaves. So compile and run. And all right, so let's enter 2. And let's see if we get the same value. Sure enough. So method 1 using for loop, 2 factorial is 2. Method 2 using for loop, Stirling, 2 factorial is 2. And then we can run it again. This time I don't need to compile. The program is just fine. I'm going to do factorial 5. So let's see how close that is. Okay, so factorial 5 is 120 using the for loop. And factorial 5 using Stirling also shows 120. Right? So in the ballpark, we're the same. Now, if I had shown the actual precision, we know there is a difference between them, right? So again, remember, Stirling is an approximation. So what's the lesson out of this? The idea is that functions have a place. They're very important because they allow you to zero in on a specific algorithm and just focus on it separately, and you may or may not run it at all. We're going to be doing a calculator example in the next video or the next lesson with some UML diagrams to explain the concept of extend and include. So we're going to get into what we call software engineering a little bit. So I'm going to up the game now as we move forward. We're going to see more and more unified language that we use for modeling and then write code. So we're going to do a lot of prep work before we actually write code. Because now, as you can see, we have to be a lot more strategic, especially if you're doing procedural or object-oriented programming, which will be in another series of lessons. And you're going to find yourself spending a lot of time planning before you code, right? Because then you can decide what will be the best approach to solve a problem. And to do that, we're going to go through simple life cycles of what will be needed to complete an application. And that will give you hints on how to handle much larger projects than an example like this. Okay, so I will see you in the next video, and it's going to be an exciting introduction to software engineering while we're doing simple examples. And our next example would be a use case with the concept of extend and include, and then we get to see how these functions come into play and how we use them. I will see you then.